Alright, you're welcome again, and today we'll be looking at fields, rings, subrings. And for the first aspects of field is where we get to note that it's performed under two binary operations, which is the additive operation plus and multiplicative operation times, or denoted as dot. And for set G to be a field, we should know that it contains these three properties, and the first is G under plus must be an abelian group. I know an abelian group contains five properties, closure, associativity, inverse identity, and commutativity. And then the next part will be where G subtracting the zero element is also an abelian group but performed under the multiplicative operation. So we get to look at an example of this in the next video. And the last property is this G, set G under the two operations satisfying the distributive law. And the distributive law here states that A dot B plus C must be equal to A dot B plus A dot C. And we will be looking at that also in the next video. Then another aspect of this tutorial today will be looking at rings, and rings are also performed under two binary operations, the additive and multiplicative operation. And we need to know that G is a G to be called a ring. This part ring is actually an abelian group. So G under plus will be an abelian group, and under multiplicative operation will be a semigroup. Now a semigroup is different from a subgroup, and a semigroup contains two operations, which is a closure and associative property. And then we need to note lastly that for a ring to be commutative, we need to have G under the multiplicative operation to be commutative. And then if this is a commutative semigroup, then we have the ring G to be commutative. So the last part we'll be looking at will be the subring. Subring, we get to have two non-empty sets, S and R, and we'd like you to know that S is actually called a subring of R if R itself is a ring and defined on two binary operations, which is this additive operation and the multiplicative operation. And we need to know that S must also be defined on the same operation, which is the additive and the multiplicative operation. But S is actually a ring and is actually a subgroup, just let's say a subgroup, but a sub is contained in R, so it's actually going to be called a subring of R because they are both rings, but R S is. So like I was given an example here, like let's say for example R is equals to set of 1, 2, 3, 4, and we have S to be equals to 1 and 2. If this is performed and on both operations and we get this as a ring, and this also is performed and we get this also as a ring, then we can say S is a subring of R because you see 1, 2, 1, 2. Everything contained here, it's inside this. You understand that? So that will be all for this video. Thank you for your subscriptions. See you in the next one.